This is DSMA 3. We will be talking about equivalent fractions. Let's take a look at this graphical image that we have. So we have one circle, the very first circle, and half of it is shaded. So notice the fraction below it is representing 1 shaded out of 2 equal parts. On the second circle, we have 4 equal parts, 2 parts are shaded. So the fraction that represents that is 2 over 4. And the next one is 6 equal parts. 3 of those are shaded, so 3 over 6. And the last one is 4 over 8, or 4 shaded parts out of 8 equal parts. So notice that if you look at the circle, we worked with one circle on each of the fractions. The shading did not change. It stayed in the same regions. The one shade was the peach side, the other is the white side. So each of those fractions, since it is dealing with the same image basically, just has different equal parts, those are called equivalent fractions. So if you look at 1/2, in order to change 1/2 into a 2/4, what they did was they multiplied the numerator times 2 and the denominator times 2, and they end up with 2 over 4. All right. If you take a look at the 1/2, and what did they do with the 1/2 to make it look like a 3 over 6? They multiplied the denominator and the numerator by the number 3. So as long as you're multiplying the numerator and denominator by the same value, then you're creating what's called an equivalent fraction. We will talk further about this as we move along in this lecture. Write a fraction to represent the shaded part of the figure. So in this case here, what we need to do is to count how many equal parts that we have. And I'm just going to go counterclockwise here. 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 equal parts. That means our denominator is 8. And it says the shaded part of the figure. So the part that's shaded red, there are 7 shaded parts. So the answer for this is 7/8 is the fraction that represents the shaded part of this figure. Represent the shaded part of the group of circles with an improper fraction and a mixed number. So we have 2 items to do. What we want to do is take a look. We have 3 circles, but you want to make sure that each circle has the same equal parts. So each circle is divided into 4 equal parts. The 4 equal parts is the denominator. Next, we're going to count the shaded region. So 1, 2, 3, 4, 5, 6, 7, 8, 9 shaded regions. So 9 shaded is your numerator over 4 equal parts for each of the circles. So this leaves you with 9/4, your improper fraction, as your answer here. Now remember, for an improper fraction, you have your numerator, which is greater than your denominator. That will give you an improper fraction. All right, so for the second part, it says the mixed number, which represents the shaded region. You have 2 ways to look at this. The first one I'm just going to demonstrate by looking at the actual images they gave us. So I'm looking at reference to the shaded region. I have 1 hole shaded, 2 holes shaded. So I have 2 as my whole number. On the last part here, the last circle, I have 1 shaded out of 4 equal parts. 1 shaded out of 4 equal parts, 1/4. So in this case, 2 and 1/4 would be my answer for the mixed number. Now, if you didn't want to look at the image and you totally trusted your improper fraction, you could have done some long division if you chose to. You can take your 9/4 and do long division. So I'll just make a little arrow here. 4 divided into 9. goes twice. 2 times 4 is 8. And subtract. My remainder of 1 is going to be rewritten as remainder of 1 divided by the divisor number 4, or 2 1/4. All right, so either way, you can do the long division or you can look at your image and get your mixed number. Once again, for this problem, we will represent the shaded part of the group of figures as an improper fraction and a mixed number. So we have these 6 egg-shaped figures. They are each cut into 2 equal parts. So the 2 equal parts is your denominator of 2. And then what we'll do is count how many are shaded. So I'm just going to go through here and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have to write a little smaller here, and 11. So we have 11 shaded out of 2 equal parts for each figure. Remember, the 2 is just by looking at one figure and noticing that they have equal parts of 2. All right, so this would be 11 halves, which is your improper fraction representing the shaded region. Next, we'll go back and you could take a look at the image one more time and count how many whole eggs, if you will, are colored. So I have, here's 1, 2, 3, 4, 5 fully shaded. That's my whole number. And on this very last one right here, that is 1/2. 1 out of 2 equal parts shaded. So 5 1/2 represents the mixed number. Once again, you can always take your 11 halves and do the long division. You will come out with the same answer, 5 1/2. Determine whether the pair of fractions is equivalent. So in order to determine whether they are equivalent, we have a process called cross product that we can use. So what we do is set this up as 4/8 equal to, because we want to prove that they're equivalent. I'm going to place a little question mark right here because I'm trying to prove that they're equivalent. All right, so cross product, the word product means that we're going to be multiplying. Cross means that we're just going to go across the equal sign. So the first thing I'm going to do is take the numerator of 7 and multiply it by the denominator of 8 and set it equal to the numerator of 4 multiplied with the denominator of 14. So let me rewrite what I just said. 7 times 8 equals to 4 times 14. So if I multiply 7 times 8, I will get 56. And if I multiply 4 times 14, I will also get 56. So since this is a true statement, the left side is equal to the right side, I can say that these are equivalent fractions. So when the left side equals the right side after your cross product, the fractions, the original fractions I gave you, are equivalent. We will continue to practice over the next 2 slides. This one is determine whether the fractions are equivalent. So once again, I have 6/11. I'm going to set it equal to 12/22. I will do my cross product and see what we come out with. So I have 11 times 12 is equal to 6 times 22. So 11 times 12 results with 132. And 22 times 6 results with 132. Again, we have a true statement, so these items are considered equivalent. Now be careful because they switched the order of the answer here, and it says the fractions are equivalent is now answer B. Again, we used the cross product to prove that these fractions are equivalent. If the answers are not the same, then it is considered not equivalent. Determine whether the fractions 2/6 and 7/21 are equivalent. So once again, we can do our cross product. I will just set this up. 2/6 is equal to 7/21. We will complete a cross product, which will give me 6 times 7 on the left here equal to 2 times 21. So 6 times 7 is 42, which is indeed equal to the right-hand side. 2 times 21 is 42. That gives us that true statement. So we need to select either A or B. And let's take a look. It says A, the fractions are equivalent because the product of the numerator of the first fraction and the denominator of the second fraction is equal to the product of the numerator of the second fraction and the denominator of the first fraction. That is, the cross product for each multiplication is. So the cross product are these end values here, the 42. So that's what you will place in here is 42, and we're going to select A because it's saying that they are equivalent. Option B says that the fractions are not equivalent, which is not true. Write the fraction in lowest terms. So another way to write this instruction, you may just see simplify. So when you simplify, you may think, oh goodness, that's order of operations. But it also means to reduce to lowest terms. So when we take a look at each of these values, 21 divided by 27, what may help some of us is to look at what's called a factor tree. And that's where you take a number and break it down to all the possible numbers that the lowest number, smallest numbers, in which you multiply to create that value. So if I took a look at 21 and I know that 3 goes into 21 7 times, both of these are prime numbers. So I know that 21 cannot break down smaller into prime factors other than 3 times 7. Right now, if I take a look at the number 27, I can also notice that it is a 3 times 9. And then the 9 breaks into 3 times 3. So if I wanted to, on here, the prime factorization, this would be considered as 3 to the third power. It's called the prime factorization. And over here, it's just 3 times 7 is the prime factorization. But I really don't need to break it down that far since I see that I have the 3 and the 9. I'm just going to use 3 and 9. 3 times 9 is 27. The reason why I'm stopping with just that 3 times 9 is because I noticed that I have a 3 in the numerator and a 3 in the denominator. When you take 3 divided by 3, we call this dividing out. 3 divided by 3 is 1. If you wanted to, you could rewrite this separately. This is 3 divided by 3 times 7/9. It is the same thing as what I have listed above it. And 3 divided by 3 is just 1. All right, that leaves you a nice 1 in the numerator and the denominator here. And 1 times 7/9 is just going to give you 7/9. So 7/9 is called simplifying or reducing to lowest terms. That's using the factor tree. Another way you could have done this is to take the 21/27, and some people just notice that both of these are divisible by 3, so they will divide each number by the same value. Once again, it has to be the same value. And if you divide each of these numbers by 3, 21 divided by 3 leaves you 7, 27 divided by 3 leaves you 9. You will get the same answer. So either one of these options will work. So once again, we are reducing by simplifying the fraction or reducing to lowest terms. So in this case, look at the instructions, write the fraction in simplest form. So we have 12 divided by 54. And again, we can go grab our factor tree. So take the number 12, break it apart, You can say 3 times 4, 2 times 6, however you want to do it, but think of two numbers that multiply together to give you 12. I'll go for the 2 and the 6. 2 is a prime number. I know it cannot break down any further. And 6 breaks into 2 times 3. All right, so this is 2 times 2 times 3. That's the prime factorization. Then I'll take a look at the number 54, and I can break this down into 2 times 27 will give me 54. Again, 2 is prime. I can take the 27 as we broke down on the previous problem, 3 times 9, and 9 breaks into 3 times 3. So I'm just going to write all these out instead of using the exponents. So these are the prime factorizations. So if I wanted to, 12 is 2 times 2 times 3. And 54 is 2 times 3 times 3 times 3. What we do next is divide out what's in common. 2 divided by 2 is 1. And I can take out a 3 in the numerator and denominator. 3 divided by 3 is also 1. And what that will leave you with is a 2 in the numerator, and you have a 3 times 3 in the denominator. So my result is 2/9 for my simplest form. And once again, if you didn't want to do your factor tree, you can break it apart slowly. You can look at both your numbers and notice that, hey, these are both even numbers. Let me divide both of them by 2 since they both are even. So if you divide these numbers by 2, you're going to get 6 over 27. And then you may notice that both of these are divisible by 3. So you can divide by 3 and divide by 3. 6 divided by 3 is 2, and 27 divided by 3 is 9. So once again, you have the same result. Two different ways to work the same problem. Find what works comfortably for you and stick to that way all the time. So one last problem with reducing to simplest form. We have 32 divided by 25. Now, although this is an improper fraction, it's not asking us to write it as a mixed number. So make sure you read these instructions where it says type an integer or a fraction. It did not ask for a mixed number. So one of the things we can do here again is the factor tree if you like. We'll take 32 and let's see, I'm going to use 4 times 8 is 32. I'll take my 4 and break it into 2 times 2. 8 is 2 times 4. I'm going to circle these because these are prime numbers. 4 will also break down into 2 times 2. So it looks like I have a bunch of 2's. This is actually 5 2's. Or you can say 2 to the 5th power, same thing. And then the other number is just 25. And the only number to create 25 is 1 times 25 or 5 times 5. And 5 is a prime number. So this is 5 times 5, or we can say 5 to the 2nd power. So you can see that if you were to write these out, it wouldn't make any sense to do this because in the numerator, they break down all to 2's, a base 2, and in the denominator, it is a base 5, only 5's. So obviously, there's nothing in the numerator and the denominator that are in common to divide out or cancel. So therefore, your original fraction is the answer. And you would place 32 over 25 in for the answer. For this last slide, we're going to discuss reciprocals. So if this is your original fraction, I'll just put down original right here, this 3 over 4, the original fraction, the reciprocal is just to flip it over or to invert it and write it as 4 over 3. All right, this is also called, reciprocals are also called the multiplicative inverses. Multiplicative fancy name for reciprocals. All right, so for instance, let me give us a little table here for some examples. Say the fraction, my original fraction, and then we'll say reciprocal. All right, so if I gave you 5 over 6 and I asked you to write the reciprocal, you would just invert it and give me 6 over 5. And if you want to check this, all you have to do is take the original fraction times the reciprocal. When you multiply those two fractions, you should get the answer of 1. That way you know that you did this correctly. And it's a positive one. So if I gave you a negative 1/2, the reciprocal is a negative 2 over 1, which can be written as negative 2. A negative times a negative will make it a positive, and 1/2 times 2 would make that a positive 1. Again, if you multiply the fraction times the reciprocal, you should get a positive 1. If I give you 5, what you can do with this 5 is to rewrite it as a fraction. So say it's 5 over 1. And that way, when you write your reciprocal, you will flip it and give me 1/5. All right, so that is what we call reciprocals or multiplicative inverses.